Hello guys, I'm Andrew Pfefer, and this is my presentation of Avadelli Automobili. I am a graduating senior. I've been in the Technology Student Association for about 4 years now, and I'll be attending CU Boulder for aerospace next fall. And as a side note, this class as a whole is really what drove me to aerospace. I was kind of lost at the beginning of the year, and so once I chose what I wanted to do and went through that process, it really helped me understand what I wanted to be. And so if you ever have an opportunity to do something that you like to do, take advantage of that because that helps you find yourself. Let me start with my logo. As you can see, it's an A, B with an arrow through it. And I'll start with how I chose the name Avadelli Automobili. So I took inspiration from famous companies like Ferrari and Lamborghini. They're Italian names, they're strong, and so I looked up common Italian surnames. And the first one that had an A was Avadelli, and Automobili stands for car. So it just it went together really well. I chose AB because it was the first 2 letters of Avadelli, and because it doesn't have any connection to any other company. I then chose the gray gradient in the AB because it signifies metallic or metal and better quality products. And for the arrow, I chose a red gradient because that represents speed. And of course, the arrow is increasing towards the right, so speed. About myself, I'm a car enthusiast. I watch Top Gear, I know a lot of other people do, and I read magazines, and just throughout my life, I've just become accustomed to these machines. I love cars that push the limits of speed and aerodynamic efficiency, reaching for those fastest accelerations and fastest track times. Likewise, in the aviation or aerospace field, planes that have the best, that strive for the most stealth or the fastest cornering, and rockets that have the largest payloads. So I was kind of in a position where I wanted to connect my automotive interests with my aerospace interests. And it wasn't that hard to think of a spoiler. And if many of you haven't seen a spoiler, most of the people have seen a spoiler on the back of a car. Many of the ones that you see in parking lots, in like Grandview parking lot or other places, are just for aesthetics. They don't actually do much. But ones on cars such as this, which is a Bugatti Veyron, or this car, which is probably a racing car, and of course F1 cars, actually help the car to go faster. I'll get into a little bit of the aerodynamics later, but the reason it does is it gives it more traction in the back wheels by pushing down on the wheels and allowing the car to get more grip. So my project objective was to learn how spoilers work, which I had a pretty good idea, but I wanted to get more in depth. Get my CSWP, which stands for the Certification in Solidworks Professional level. I already had gotten my certification at the associate level, but I wanted to up that. I wanted to create a functional model that would then run and simulate what the full-size one would do. And I wanted to use the job shadow that we had to do in class to then learn about the field of aerospace, or I thought I was going to do mechanical, but I changed to aerospace, and possibly get an internship through that. Finally, I wanted to use my project as a way to show colleges of my interest in the field of engineering and possibly my work ethic. So the first thing I had to do was choose a timeline. And it was kind of a difficult thing to do. I hadn't done any research on the project, or I didn't understand how to break such a big task up into little chunks. So I started with what I knew. I would have to research, I would have to design the object, I would then have to test it to verify that what I had designed worked, and then I could print it, assemble it, and then program it. And it's kind of funny knowing that at the beginning of the year I had no idea how to code. I also didn't know how to 3D print or test things in SolidWorks. But I knew that I'd learn that on the way. I then divided the 7 months up across and put my initial presentations, mid-year presentations, and final presentations within it. This was just a guideline. I'll go through my actual timeline. October was mostly just starting the research, finishing up the other presentations that we had to watch. November was my design month, so I was just going to design throughout the whole thing. And December was finishing up design and catching up. I did complete all of these within the time. It was I did a lot more research at the front, so I had to crunch the design at the end, and in fact, it ended up me on winter break designing a lot, but I did get it done. For January, I wanted to start 3D printing all the pieces. I was hoping that I'd get all the pieces done within January, and I'd give myself a little bit of February to print, and then I would start to wire the model within February. And in the middle of February, I was going to start the process of coding, and then finish the coding throughout the month of March. And April would become my presentation, getting ready for my presentations. And as a matter of fact, of course, this timeline didn't pan out. I didn't know from the start what I was going to do, but once I found my way, it ended up my assembling of the model took way more time, and the coding took less time. So that was just an addition to it, or a correction to it, but it still worked out in the end. I'm going to move on to what I did in my project. I had to learn Flow Simulator within SolidWorks. I was proficient in SolidWorks before this class, but I had no idea how to use a Flow Simulator, which is within the program, and it simulates how the air flows around objects so I can optimize its aerodynamic capabilities. I didn't know what an Arduino board was, and so I had to look into that, how to code it, everything along the lines of the computer science / electrical engineering. I had never used a 3D printer in my life, so I had to learn how to 3D print something, and I needed to look into the componentry of the servos and the wiring between them. So now I can go into how wings work. I wanted to explain to you guys how they work so that my project makes more sense, but I wanted to start with an airplane wing because that's what most people are familiar with. So right here, I have a cross-section of an airplane wing. On the top of the leading edge, which is the front part of the wing, actually splits the air coming in. The air that goes over the wing is moving slower and has a lower pressure because of Bernoulli's principle, versus the air that goes underneath, which is moving faster, which has a higher pressure. The high pressure on the bottom and the low pressure on the top creates a net force upwards, which creates lift, which is why an airplane can fly up in the air. But for a spoiler, I don't want my car flying, I want it pushed into the ground so it has more grip. So what I'm going to do is I'm going to flip it. So it's the same cross section, just upside down. So the high pressure is then on top and the low pressure is on the bottom. The net force is downwards. Here's a picture of how air flows around the wing. That'll come later up in the presentation. I just wanted to show a general sense of what it does. I had to choose a wing shape. There's many different shapes of wings out there, and they each do a different purpose. I ended up choosing an existing wing shape because I wanted to show that anything that I did, anything I improved to the existing shape was not because of the existing spoiler as a whole, was not because of the shape I chose, but because of the additions I made to the shape of the wing. Here's a little schematic of what the pieces are of a wing. It's a little more complicated, but this gives a little snapshot. You have the chord line, which just runs from the leading edge to the trailing edge, and then you have a few lines to that then create that difference in speed of the air. The angle of attack, I didn't think was going to be as important as it actually was. In fact, a wing is able to vary the amount of lift or downforce for a spoiler it can create by the amount of, or the angle of attack. And all the angle of attack is the angle between the chord line, which is that line between the leading edge and trail edge, and the inflowing air. So if it has a 0 degree angle of attack, which is close to that picture on the edge, the air just flows around it, and it doesn't create any lift at all. However, if I increase the angle of attack, there's that, you can see that large difference in the distance the air travels across the wing, which then creates that difference in speed. And however, if you increase the angle of attack too much, you see a separation of the air. and it actually will stall the wing, which means that the air doesn't actually meet up to itself at the end, and you get massive amounts of turbulence and vortexes, which causes the wing to not create any lift at all. So if you were in an airplane, the airplane would just fall out of the sky because it has nothing pushing it up. Of course, for a car, this could be beneficial for braking. So if you were to stall the wing upwards, the car's not going to fall out of the sky because it's already on the ground. It'll just help brake the car, make the car stop quicker. So originally I wanted to create an equation for how the wing would move based on inputs like steering and acceleration. But I realized that that kind of equation would need data that you could only get through computational fluid dynamics, which is a master's thesis, and something that would not be within the scope of my education. Perhaps when I move on to the aerospace field, I will come across those topics. So I had chosen to just go for a simulation, which I have for you guys later. So to start out with my project, I created some sketches. I knew I wanted to create a new type of spoiler. Initially, I thought I was going to change the cross-section of the wing by allowing the wing to actually fold up or stretch out, depending on what speed it was going at or what it wanted to do. And also, I wanted to raise it or lower it. And in fact, I came across a turning point in my research and my understanding of wings that changing the cross-section wasn't necessarily the most efficient thing to do, because you choose a cross-section for its efficiency over a span of speeds, a range of speeds. So I decided that I would change the angle of attack, because that's much easier to change and it's more variable, it's overall more effective. I then started creating some, practicing my skills of creating wings in Solidworks. I started out with just taking a cross-section and extruding it or extending it in the program. I then worked on bringing the sides up because I wanted not only a force downwards, but also a force in the down and outer edge direction, so that as the car went around a corner, it would have force downwards, but also towards the inside of the corner, so you could get faster speeds without losing traction. But I also wanted that side piece to be recessed backwards a little bit, so that when the wing was forward, those side pieces weren't facing the ground, they were facing forward. So I recessed it backwards. My overall results, I created the entire model in SolidWorks. As you can see over here, I have the flat part of the wing. I then have the side section that does have a cross section, so that it does create the force towards the, in this case, left. But then I have a horizontal piece. And that is really important because I had tested the rest of the piece and I saw massive amounts of turbulence on the outer edge because all of the high pressure up here and down pressure over here, or low pressure, started to, the high pressure started jumping around and it created vortices, which are very inefficient on a wing because it creates a lot of drag. So when I put those horizontal pieces in there, it massively cut back on those vortices. And as you can see, I can articulate that edge so that I can create a higher angle of attack over here than on the rest of the wing as a whole. So as I worked, I started printing, and I was very happy with the prints. They came out very similar to my models in the computer, but they did take a while. This piece total probably took about 5 to 6 hours, because it's 2 different pieces. So there was a lot of time spent, and the total number of pieces on my model is about 10. So it took a very long time to start printing these. I had tested it earlier, but I wanted to show you guys my tests. These lines represent the airflow over the wing. The red indicates high pressure, and the blue indicates low pressure. It's kind of hard to tell here, but this whole section is blue. And if you were to draw a line from the high pressure, the red, to the blue, the low pressure, It would be a vertical line downwards, which is exactly what I wanted, because I want the wing to be pushing straight down. This is another view of it. You can see the air on the top is moving close to straight, but as it hits the wing, it follows the wing's shape, and then that pressure is going to push upwards and staying on the bottom, and that is what creates the downforce. This one's important because this shows the vortexes I was talking about earlier. If you look right here, the air is moving almost straight through the wing, which in an ideal world is what you always want to happen. But in fact, as you move across the wing, the aspect ratio of the wing starts to make the air push out to the side. And once it reaches here, starts to vortex or turn into a spiral. And that is what creates drag. These winglet tips that became horizontal actually cut down on the amount of vortex that I got. But everything is great in the computer, but I needed to take it to the real world to verify that what I was getting in the computer actually would pan out in real life. So I made a scale model of my wing and brought it to the wind tunnel at Eaglecrest. I tested it at about 77 miles an hour, and I was really afraid that this little piece of plastic was just going to break off and fall into the back of the wind tunnel because it's such a small piece. But in fact, it never did that. It stayed perfectly still. It didn't even wobble, and my results were better than expected. So on this graph, you can see the lift as the red and orange, and as the speed increases, so does lift. And when I say lift, I mean negative lift, which is drag. This is just the magnitude. And then you have drag on the bottom, which does increase, but the ratio, or the lift to drag ratio, was negative 3.33, which is very impressive. What that means is I get 3.33 times more downforce than I do get drag. And as you guys know, engineering is a measure of cost versus benefits. And so I got way more benefits for the cost of drag. So I would say that this was a successful test. But then I tested a scale model, the same exact scale, at the same angle of attack, but the left edge was articulated about 10 degrees. And I got even more interesting results. It created more lift and a little more drag, but the ratio was constant, a negative 3.19, which is very close to negative 3.33. But that was very important because if I articulated the side, I got more downforce, which is what I wanted, because then I could get that torque on the side. Unfortunately, I wasn't able to test that just because of the capabilities of the wind tunnel. So everything about a small scale test is great, except for I wanted to know what it would be like for the full model. So there's this thing called a Reynolds number, which is a non-dimensional value that allows you to compare scale models of objects. So you can test a tiny car and know what the big car would do, or you can test a tiny wing and know what the full wing would do. So I put the velocity and chord width and all the other data about my small test into the Reynolds number calculator and got 60,338. So if I wanted to know what the full wing would be, it has to have the same Reynolds number. And so since the kinematic viscosity of the air would be constant, I would know the chord width, which is about 6 times of the scale I tested at. So that means the velocity I would know the data for is 6 times smaller. So when I tested the small wing at 77 miles an hour, I tested the full-size wing at 13 miles an hour. So if I wanted to know more about the full-size wing, I would have to have a wind tunnel that had a larger capacity for its wind speed. So outcomes achieved, I created a full functioning model. I also created a working code so that that model demonstrated exactly what I would want it to do. And I actually have that demonstration for you guys today. So I'm going to switch over. I have a YouTube video to play on the screens, and this wing is going to react to the video as if it were on the back of the car in the video. plug in the model, it's going to calibrate, and then I'll start the YouTube video. Lags a little bit, so the timing is a little off. But I have a full functioning model that reacts to how I want it to. And this is, for me, a very important part of my project because it's not only the designing of the wing in SolidWorks and printing it, but it was also assembling it and also doing the electrical engineering slash computer science portion of the project, which was to then wire it up to an Arduino board and program that board so that it would move. Which I came a long way from the beginning of the year not knowing code at all to being able to control the servo motors in this model. There were a few roadblocks on my way to here. SolidWorks, for the first few months, wasn't working properly. The airflow simulation, I wasn't able to use that on some of the, or on all the school computers and on my computer at home. But eventually I figured it out. Only a few computers were able to use it, and I was able to do my tests on those. 3D printing, there's always going to be issues with 3D printing. Some of my classmates have had issues too. One of my pieces stopped printing at about 91%. It was so close to being done, but it was actually became a benefit because I now have it on my table to show people what the inside of a 3D printed object looks with its hexagonal or honeycomb structures. So I really wanted to thank my advisors. Without them, I would not have been able to get here. Their suggestions were just so important and vital to my project, whether it be the Reynolds number or anything about aerodynamics. Mr. Stephen Gorley, who's here today, he's an aeronautical and astronautical engineer, graduate of MIT, and just his expertise in the field of engineering was invaluable. Mr. Ken Sarnowski, who's a programming teacher here at Grandview. I'm in his class for AP Computer Science, and I learned everything I know about coding from that class and from him. So without him, I would not have been able to even make this thing move. Support advisors, my dad, Victor Pfefer, Tyler Dugan, my friend, Alexa Lehrer, my friend, and Christian Frank, my friend. Also, one of the most important pieces of my project was my jog shadow. See, like I told you guys earlier, I wasn't quite sure if I wanted to go mechanical or aerospace. And so I reached out to one of my mechanical mentors from a program I'd done in the past, and he talked to someone, and eventually I got John Mark Antonio's number. And he actually is a recent graduate of CU Boulder. He got his master's degree, and right out of college went to Lockheed Martin to work. And so I followed him around for a day, and he showed me what engineering really is. Because if you walk around this room, you'd think, oh, engineering is building an object, testing it, doing all this stuff, without actually going and writing up why you're even doing this, reports, all this. I found out that engineering is really a writing, it has a large writing component to it. We do, in this class, do binders and journals, but I didn't understand the extent it was in the real world, this was very helpful. I also didn't know the teamwork aspect of engineering. This guy, he worked on a team with like 7 other engineers just to work on this tiny little piece of the Orion spacecraft. It was the ejection module. But this was invaluable to me. So here's my bibliography. It's only a few slides. Thank you. Do you have any questions?
I would assume if you were to go to a market like this, what kind of material would you use for the spoiler as opposed to plastic?
Good question. So I could potentially use 3D printed material, but like you said, it's not necessarily the strongest. There's other materials such as carbon fiber or aluminum that are much stronger and are still lightweight. And as if you look on the market, a lot of spoilers are on carbon fiber, so it's a proven object. It's used all throughout the aerospace field. And then you can use aluminum to reinforce that, especially in the supports and maybe across the whole wing to give it some extra rigidity. Any other questions?
If you were to take this to market, would you sell it to
the use of this spoiler would be definitely for racing. You don't need a spoiler in general unless you are looking for that racing advantage. And so if I were to bring it to market, racing companies or F1. Also, there's a lot of cars like Bugatti or Koenigsegg, which already have them in their road cars, so you could potentially sell it to them, license it, or something to that matter. Any other questions? Yes?
On an airplane wing, would they have that piece that goes up, like your spoiler does?
Mm-hmm.
The purpose of that is for?
So, good question. On an airplane wing, there are winglet tips, and they do serve a similar, I'll explain. So on a airplane wing, those little wing tips at the end are a wall, essentially, between the high pressure on the bottom of the wing and the low pressure on the top of the wing. Otherwise, you'd see that kind of skipping around the edge, and then that would create those vertexes. So if you had that little wall there, that stops it from doing that as much, right? And so on my wing, these wing tips that come up here, those actually create those have a cross section, so those are creating the high and low pressure. So I needed to then flatten it out, just like the wing tips on an airplane, but these ones were horizontal. Any other questions?
All right. Well, thank you very much. Good job.